This video is about designing a passive RC filter. The example is taken from section 11.3 of the Applied Analog Electronics textbook. Now, the filter we want to design has to pass through the frequencies that are relevant for a blood pulse. And it needs to block DC so that DC doesn't get amplified, and we only are amplifying the pulse signal. All right, well, what are the frequencies for a pulse signal? A lot depends on how much detail we need in the pulse signal, but the basic fundamental pulse is somewhere between, say, 30 beats per minute and 180 beats per minute. What is that in hertz? Well, 30 beats per minute is half a hertz, 1 beat every 2 seconds. And 180 beats per minute is 3 hertz, 3 beats per second. So we can give a specification for our filter. We want to pass 0.5 hertz to 3 hertz. And we want to block DC. Now, I'm not saying anything about what happens outside the range 0.5 hertz to 3 hertz. Essentially, I'm saying I don't really care what's happening there, except for the DC has got to be completely blocked. I want a gain of 0 at DC. Well, DC blocking is a high-pass filter. So we're going to need a capacitor to block the DC, and then we're going to need a resistor to recenter the output at the voltage we want when there's no input, so the reference voltage. Okay, so there, our circuit's designed, except for one little problem. I don't have component values. Always need component values. So let's take a look at the Bode plot for this high-pass filter. We have got, at high frequencies, the gain is 1. And then we've got that it drops off a little bit, sort of a rounded corner there, and at low frequencies, the gain is going to be j omega RC over 1 plus j omega RC, which, when the frequencies are low enough, is basically just j omega RC. So if we just look at the magnitude of that, the gain here is omega RC. So there's the place where these two come together here, the corner frequency, and that's going to be 1 over 2 pi RC. Okay. Now the question is, when we're doing this design, where do we want the 0.5 hertz to 3 hertz to appear on this plot? Well, obviously we don't want it down here. We want it to be in the pass band up here, so above the corner frequency. And the biggest question really is, how far into the pass band does it have to be? Do we care if the 0.5 hertz is attenuated a little bit? Because remember that at the corner frequency here, the gain at that point is 1 over the square root of 2, which is approximately 0.7. So we've got 30% attenuation at that corner frequency. Is that a problem? Who knows? Didn't give you enough information in the design spec to say whether that's a problem or not. If somebody just says, I want to pass 0.5 hertz to 3 hertz, usually, if they're an engineer, what they mean is that they're willing to go up to this 30% attenuation in that range. Not always. Sometimes they say, I want it flat in the pass band, and then you need to be higher frequency. So let's actually do two designs. Let's do one design where we put that corner frequency right at 0.5 hertz, and then 3 hertz is somewhere up here. And let's do another one where the 0.5 hertz to 3 hertz is higher up here, so that the pass band that we're interested in, the 0.5 hertz to 3 hertz, is flatter. Let's make that 3 a little more 3-like. And how far up do you have to go to be pretty flat? Rough rule of thumb is a factor of 5 away from the corner frequency, and the straight line approximations are really good. They're within like 1%. So then we would put the corner frequency, instead of putting it at 0.5 hertz, we'd put it at about 0.1 hertz for the corner frequency. So we've got two designs, one with a corner frequency of 0.1 hertz and one with a corner frequency of 0.5 hertz. And for this one, we really want the corner frequency to be at most 0.5 hertz. Because if the corner frequency is just a little above that, then we're attenuating more than the 1 over square root 2, and that's now violating sort of what we would accept as passing the frequency. Okay, so two designs. What do we need to do? We need to figure out what's R, what's C. Let's start with what's RC, because we can do that here by just looking at, well, take the corner frequency, multiply by 2 pi and invert it to get RC. So here, RC, actually, let's just say this is approximately. We don't need to be exactly at 1.1 hertz. So RC is going to be about, let's put 0.1 hertz, multiply by 2 pi, and invert. So that's about 1.59 seconds. And I'll do the other one later. Okay, so we now know what R times C is. What's R? What's C? And the answer is, well, there's a lot of choices. How do we choose among them? And I'd like to give you sort of a rough rule of thumb for that. And that is, we generally want resistors not to be too big or too small. If they're too small, then we need a lot of current for them, because to get any voltage across them, you need a lot of current if it's a small resistor. And if they're too big, you end up with noise problems sometimes, because the noise, thermal noise in a resistor is proportional to the resistance. So, rough rule of thumb, let's keep things, when we can, between 1 kilo ohm and 1 mega ohm. Now, those are not strict rules. Sometimes we'll go a little lower than kilo ohm, sometimes we'll go a little above a mega ohm, but it's a good ballpark to say, all right, if I don't know what size to do, try and keep it in this range. Factor of 1,000 there, so you still have quite a few choices. For capacitors, if we're using cheap ceramic capacitors, we don't want to get too big. About the biggest ceramic capacitors I'm comfortable using is 100 microfarads, 10 microfarads. 100 would be too big. If you're using electrolytic capacitors, you can go a good deal larger, but you don't usually want to use electrolytic capacitors in this sort of signal stuff, because electrolytic capacitors aren't very precise, and you end up with huge variations in them depending on whether they're charged or not. So we'll stay away from using electrolytics for that. 10 microfarads is a good maximum for ceramic capacitors. If you want more precise capacitors and you want to use film capacitors, 10 microfarads is already getting pretty big, and you might want to keep yourself limited to 1 microfarad or even 100 nanofarads. And at the low end, we don't want to go too small, because there's wiring capacitance and stuff like that, and if the capacitors we're designing into our circuit are smaller than the ones that we've got just accidentally, then our designs aren't going to work very well. And so probably a good rule of thumb for the sort of low-speed stuff we're doing is 100 picofarads is probably as small as you want to go. Particularly if you work on a breadboard, you've got 5 or 10 picofarads just from the breadboard. So 100 picofarads is probably about as small as you want to go. Okay, so if we're using this rough rule of thumbs and we're trying to get 1.59 seconds, well, we could take a look at what happens if we go for 10 microfarads, the biggest capacitor that we're willing to use. So if C is 10 microfarads, how big would R have to be? Well, you just take this and divide it by 10 microfarads, and I get 159 kilo ohms. Well, 159 kilo ohms is not a standard value. Whenever possible, use standard values. Closest standard value is probably 160 kilo ohms, and that's only sort of standard. The 160 is on the E24 series. If we wanted to limit ourselves to the E12 series, then we might use 150 kilo ohms. And E24 is still pretty common. That's neither one of those would be a bad choice. And the 150 kilo ohms would give us a slightly smaller RC time constant, slightly higher corner frequency, but not by much. And remember, we had a lot of slop here because we were just trying to stay about a factor of 5 away. And so if we're, a factor of 4.5 away, that's probably good enough. So we can be pretty sloppy about how close to this RC time constant we get. Now, 10 microfarads, as I said, is about the biggest capacitor I want to go. Can I get away with a smaller capacitor? And the answer is, well, I can make a bigger resistor here. If I went to 1 microfarad, then I could use a 1.5 mega ohm. That's pushing a little bit on the size of the resistor I'm willing to use, but not too badly. Or I could pick another standard value here like 2.2 microfarads. What would that be? So I take the 1.592 seconds and 2.2 microfarads, do the division, and I get 723 kilo ohms. That's not a really standard value. I could go up to 750 on the E24 series or down to 680 on the E12 series. I think 680K, stick with the E12 series, would work pretty well. Now, what would that give me? So if I do 680 kilo ohms, 2.2 microfarads, and multiply them, I would get 1.496 seconds, or in terms of the corner frequency, that's 0.106 hertz. Instead of 100 millihertz, it's 106 millihertz. That's close enough. Okay, so this actually looks like a pretty good choice to me. It's about as large a resistor as I'd want to go with, and a small enough capacitor that is perfectly reasonable. So there's a good choice. Not the only possible choice, but a good one. Let's take a look at what would happen if we went to the 0.5 hertz. Okay, so we take the 0.5 hertz, multiply by 2 pi, and invert it, and we get, now notice that we have got a constraint here. This is a less than or equal to here. So what we end up with, because of the inverting, is that RC is greater than or equal to 318 milliseconds. Okay, again we have to pick R and pick C. Well, let's see what happens if we pick C is 2.2 microfarads. So using the calculator again, 2.2 microfarads, do the division, and I get that R has got to be greater than 144 kilo ohms. What's greater than 144? The next standard value would be like 150. So 150 kilo ohms. Well, that one looks pretty good. I could go with a larger resistor here and a smaller capacitor. What happens if I pick 1 microfarad? Okay, so I take the 318 milliseconds and I divide by 1 microfarad, and I need at least 318 kilo ohms. Well, what's the next standard value? Probably about 330 kilo ohms. I could even go higher. What happens if I take this thing down to something like 330 nanofarads? Alright, so 330 nanofarads, do the division, and I need at least 964 kilo ohms, so that's 1 mega ohm. And I don't want to go any further than that because I'm already hitting up my top limit there. So here's, a couple more good designs. Any of these designs would be acceptable. there is no single right answer on a design question like this. And we'll be asking a lot of design questions like this during the course, and in most of them there won't be a right answer. There will be many decent answers, and sometimes some are a little better than others. For instance, the ones here that use a microfarad or 2.2 microfarads are going to be somewhat cheaper than ones that use 10 microfarads. Ones that go up into more than a megohm are sort of a little bit less desirable, perhaps, unless there's some real constraint that says, hey, it's more important to keep the capacitor small than it is to keep the resistor from getting too big. We won't always be able to articulate what the optimum is. There isn't always an optimum. There are decent designs which have different trade-offs. And it's a good idea to start learning what some of these trade-offs are, but for a lot of things in this course, there'll be a wide range of perfectly acceptable answers. So get in the habit of not looking for the answer, because it's very rare in this course that there is one correct answer. There'll be many decent ones.